Hello chemists, this is Ms. Placino and you're watching lesson 7.4 on ideal gases. In today's lesson we're really just going to get into how gases behave. So, goals for today's lesson. You're going to become familiar with the postulates of the KMT, in particular for gases. That stands for kinetic molecular theory, but we'll go into more detail about that soon enough. You're going to explain what conditions will lead to ideal behavior for a gas. And really the big one for today is to perform calculations using the ideal gas law. This gas law is deemed way too complex for first-year chemists according to New York State, so you cannot find it on the reference table. But don't worry, you'll get familiar with it and comfortable using it. Let's get started. Before we dive into what the kinetic molecular theory really states, let's break down what it's referring to. What does the word kinetic mean? Kinetic has to do with motion or movement. Molecular, what does that mean? Yeah, probably pertaining to molecules. So this is just a theory about molecular motion. That's all there is to it. It sounds kind of fancy and intimidating, but it's just about how molecules move. My guess is you're already pretty familiar with what a sample would look like in each of the three phases. Got a solid, high degree of organization, particles are packed close together and kind of moving around a little bit in place. Definite volume, definite shape. If we go to a liquid, we start to compromise some of those intermolecular forces. We lose that high degree of organization. We have a definite volume, but no definite shape for a liquid. We're really going to be focusing on gases. In a gas, we see no definite shape, no definite volume, and tons of motion of the particles of a gas. So that's really what we're going to be looking at today. What rules are going to determine or kind of dictate ideal gas behavior? So gases consist of particles with small volumes, really, really tiny particles that are separated by large distances. I know the terms small and large aren't very specific. Basically what we mean is the size of the gas particle itself is going to be very small compared to the distance that they're separated by. So that's what we mean with small and large distances. We'll stay focused on gas. The collision between particles and the container walls are perfectly elastic, according to the KMT. Elastic is a term that will come up more in physics. Let's just kind of break down what it means. There are two types of collisions. We can, of course, have elastic or inelastic collisions. Here's a picture demonstrating the two types of collisions. If we assume we're dropping like a ball or something, what do you notice is true about the height of the ball before and after the drop in an elastic collision? Yeah, it comes up to the same height. This means in an elastic collision, there is no net loss of energy. What about in an inelastic collision? Well, the ball is dropped from a much higher height than it returns to, so we do have a loss of energy. Yeah, maybe this is due to like friction or like the ball gets compressed, something happens, but there is a net loss of energy. We're going to assume that every time the gas particles come in contact with each other, no energy is lost, it's elastic. Anytime the gas particles hit the side of the container and bounce off, again, no transfer of energy, no loss of energy, a perfectly elastic collision. You think about this as being like you're a super high bounce ball, like it's going to bounce up and down for a long time. Pretty elastic collisions. Versus dropping a bowling ball. Please don't do that. Drop it on your foot, hurt yourself. But that is an inelastic collision. In a gas, particles are in constant, rapid, straight line motion. Gas particles will never stop. They're moving pretty quickly, especially compared to the particles of a solid or a liquid. And they're not doing any like crazy loop-de-loops. They're moving in a straight line. And our last one, pressure is due to collisions with the walls of the container. So if we're going to measure pressure, which is just kind of a unit force per area, it's all about how hard those gas particles are smashing into the wall of the container. So that does it for the KMT. Let's talk about what it means and the implications of the kinetic molecular theory. We're going to compare ideal gas particles to real gas particles. Ideal gas particles. They are not going to interact with one another. We see no intermolecular forces. And they're going to follow the other rules, or the postulates, I should say, put forth by the KMT. Real gas particles, they do interact with one another. They have intermolecular forces. And they do not follow the kinetic molecular theory. Most gases tend to behave as real gases in real life. Think about it. Think about what an ideal student would behave like. Well, let's see, they would be prepared for class every day, they'd get there on time, they'd be sitting up nice and straight in their chair, they'd have all of their notes and materials, they'd be listening, they wouldn't be talking or interrupting, they wouldn't be trying to sneak a peek at their phone to see if their friends texted. Compare that to what real students are like. Sometimes you come in late, sometimes you're tired and you're not real focused, sometimes you are dying to look at your phone to see if your friends reach out to you. Kind of the difference here. Of course, gases aren't making a choice. It's kind of about the conditions that they're under. There are ways to get a real gas to behave like an ideal gas, just like there are ways to get a real student to behave like a more ideal one. I could bring in the principal. I bet you'd be a little bit more ideal in that case. Even more extreme, I could bring in one of your parents, and you're probably going to behave as ideally as you possibly can. Sure, it goes without saying, gases don't have principals or parents to worry about. We can manipulate temperature and pressure to try to get a real gas to behave like an ideal gas. What sort of temperature and pressure conditions do we need? And all we mean is high or low. So high temperatures, low temperatures, high pressures, or low pressures might get real gases to behave more like ideal ones. Turns out that real gases will behave pretty ideally at high temperatures and low pressures. Think about what's happening under high temperature and low pressure. We've got tons and tons of space for the gas particles to move around, and they're doing so at a very, very rapid speed. Under those conditions, it's going to be super difficult for them to interact with each other. So it's going to be hard for them to establish that attractive force. And they're going to be more likely, since they don't interact, to follow the KMT. So any gas can behave more ideally if we crank up the temperature, high temperature, and we decrease the pressure, really low pressures. Years ago, a student gave me the example, this is kind of like your ideal significant other. That person is probably going to be super, super hot, but also really laid back and mellow. Not going to be stressing you out. They're going to be low pressure. So you can think about your ideal significant other. Might have some stuff in common with an ideal gas. There are two gases in particular that tend to behave ideally. Helium and hydrogen. That's kind of that's a little trivia fact there. We're going to have very, very weak intermolecular forces, so it is easiest to coax those into ideal gas behavior. All right, let's make this a little more quantitative, into some numbers. The ideal gas law applies to ideal gases, of course, and we're going to assume that all gases, regardless of their identity, regardless of temperature and pressure conditions, are going to behave as though they're ideal gases. This makes our work a little bit easier. If you take AP chemistry or any college level chemistry class, I'm sure you will address real gas behavior. We're not going to do so at this point in time. The formula that we're going to be using is PV equals nRT. Let's break down what all of this means. P is pressure. V, volume. N, it's moles. R is a constant. Talk more about that in just a sec. And T is temperature. Okay. Our gas law constant, if you were just to Google ideal gas law constant, you'd come up with a bunch of different values for R. The one that we're going to work with is 0.0821 liter atmospheres per mole Kelvin. The units of R are extremely important. They're telling you what units the other values have to be in. So for example, pressure, if I'm going to use this gas law constant, has to be in atmospheres. Volume has to be in liters. Moles, well, moles are always in mole, which is a good thing because they have to be. And finally, temperature has to be in Kelvin. You must work in the same units that are given in the constant. Volume conversions are pretty easy to do. It's usually milliliters or liters. There are some other ones that we'll worry about for pressure. We'll talk about those in just a second, and same deal with temperature. But if you're going to use this value, and this is the only one I will provide you on something like a quiz or a test, you've got to be able to convert. Really important skill. So just some conversions to know so that you're able to bounce back and forth between units. Pressure is the force per unit area on a surface. More importantly, for our purposes, got some conversions. So if I have 1 atmosphere of pressure, that's the same as 760 millimeters of mercury. That's what you'd like physically measure inside a barometer. Millimeters of mercury and torr are the same exact unit. Torr is just like an honorary name unit for Torricelli, who's credited with making like the first barometer. You also see kPAs, kilopascals. I expect you to be able to make those conversions without being given those factors. Temperature, just the average kinetic energy of a sample. This one is provided on the reference table. To get from a Celsius temperature to a Kelvin temperature, simply add 273. So a fairly easy conversion to make, but an important one nonetheless. All right, let's try out an ideal gas law question. All right, let's look at this question here in this box. An unknown gaseous sample has a total mass of 571 grams, and it's under the following conditions. You got a temperature, a volume, and a pressure. So the first question that's being asked is about number of moles of gas present. All right, well, we just learned the ideal gas law. Pressure times volume is equal to moles times constant times temperature. We know that the constant is in liter atmospheres per mole Kelvin. And if we check in the information that's been provided, we've got liters, atmospheres, we're asked for moles, and Kelvin. So we don't have any additional conversion that we have to make. I'm going to start filling in what I know. Okay, 560.0 atmospheres times 25.0 liters is equal to moles times 0.0821 liter atmospheres per mole Kelvin. And our temperature, it's hot, 1,195 K. Do I have to write my units? No, technically you don't have to include them in there. I would encourage you to put them in. It's a really good habit to get into, and hopefully it'll save you from making kind of careless, silly mistakes. It is just a math problem from here. Be careful with how you're punching things into the calculator. Pause the video, calculate the number of moles present in this sample. All right, so when I grind through the math, I come up with like 142.69. Careful with sig figs. We'll assume the numbers that I've highlighted in green, those are measured values. I see 4 sig figs for the temperature, 3 for the volume, 4 for the pressure. We're going to assume that's correct to the correct number of to an infinite number of sig figs, my constant. So I'm limited to just 3 sig figs. So I get 143 mole of gas present. All right, so hopefully that's a pretty straightforward application of the ideal gas law. Plug in your values since all of our units match the unit provided in the constant, and then it's just a math problem. Next type of question I could ask you is about the molar mass. Hopefully you remember molar mass from the previous unit. Molar mass has the units gram per mole. I got a mass in grams. I just calculated mole. Oh, can I really just do mass of my sample? divided by moles of my sample? Yeah, you absolutely can. To 3 sig figs, what's the molar mass of my sample? Getting about 3.99 grams per mole. And again, I'm really just taking the mass and dividing by the moles. That will give me molar mass. All right, and the last question I could ask, what is the identity of this gas? Well, how am I supposed to know that? You don't give me any information about that. Well, I do know the molar mass, 3.99 grams per mole. If I look at the periodic table, helium has a molar mass of about 4 grams per mole. Yeah, that's pretty close. I would say that's your best possible identification. You're probably looking at helium. If I was to ask you a question like this and it's not something like helium with 4 or hydrogen with 2, I probably have to give you some more information. I'll like tell you if it's a monatomic gas, that's going to direct you to the noble gases in group 18. If it's diatomic, I've got a handful of gases that are diatomic, but that's the way you do it. I can't give you something that's like triatomic or more. That starts just to become way too many possibilities for correct answers. All right. I would encourage you to try out the other practice problems. Those do give you some units that aren't necessarily atmospheres, liters, and Kelvin. So you can practice with your conversions and then apply it to the ideal gas law. All right. That wraps it up for today. Thank you for tuning in, and I hope you found this helpful.